Let's rewind to 1989. James Cameron's The Abyss hits theaters, and in one scene we meet the now famous pseudopod. And it's more than just a cool VFX shot. It was the first soft surface CGI character presented as a realistic computer-generated imagery that mimicked real-world lighting and materials. But what about movies that came out later, like Terminator 2, Judgment Day, Jurassic Park, or even Toy Story as the first fully CG animated feature film that came out in 1995? The answer is still no. No ray tracing or pad tracing on a global scale, and it's for the same reason that wasn't done in the past. Because even in Hollywood, the cost of computing realistic light transport was too high, which really meant it was too slow for the production pipeline. But here's the twist. Pad tracing is also expensive in game engines today, almost 30 years later. But how can that be if Unreal Engine 5 Lumen can simulate realistic dynamic global illumination in milliseconds and provide a seamless experience with 60 frames per second, so without baking, without pre-lighting or waiting? The answer is they used the same approach to calculating light transport as was done all those decades ago. They used a clever trick, something better than mere rasterization, but less expensive than full light transport simulation, like pad tracing. They used an approach where they can calculate just a few points and interpolate the rest, and that's what this lecture is all about. Hey, my name is Marco, and I'm trying to understand how Lumen works, and in this video of our real-time global illumination lecture series, we're continuing our journey from the fundamentals of basic lighting and rasterization, as well as ray tracing and pad tracing, two techniques that give us accurate lighting but are too expensive in real time, and we are shifting gears in exploring how to store and reuse lighting, how to cache irradiance, use probes to avoid full calculations, and how methods like spherical harmonics and octahedral mapping led to the screen space probes and radiance caching as the backbone of Lumen's hybrid approach. Hey, future Marco here. So after recording and editing this whole lecture, I realized something. It was over an hour long, and even I struggled to stay focused. And I already know what it's about. So to make things easier to digest, I decided to split the lecture into 3 shorter, more focused videos. The first one will cover irradiance caching and environment probes, setting up the foundations for all the rest. In the second part, we will focus purely on spherical harmonics, their power and limitations. And then finally, in the third part, we will explore radiance caching, which is the piece that makes Lumen's screen space probes work in the first place, and then the rest of Lumen itself. In this video, we will focus on irradiance caching and environment probes. But before we answer these questions, we should start with the basic one. What is irradiance? Irradiance is the total amount of light reaching a surface per unit area, and there's no directionality. It doesn't matter where the light comes from, just how much of it arrives at a point. So irradiance is the kind of measurement that diffuse surfaces care about, and why it is a useful approximation of a lot of global illumination, which is made out of direct and indirect lighting. But in most real scenes, the direct lighting is easy to calculate. It's the indirect, the light that bounces off walls, floors, ceilings, that becomes expensive to calculate. And while irradiance is a great way to approximate how much light hits a surface, computing it with pad tracing requires shooting dozens of rays per point. That's where this next idea comes in, one that changed how indirect lighting was handled for years. And that is irradiance caching. So, how does it work? We can start by observing the direct and indirect illumination for a room like we can see here. And now, since we are interested in advancing the computation of indirect lighting, let's focus on this image and notice that the indirect lighting is coherent, which means it changes slowly over a flat surface and more rapidly on curved ones or near edges. Now, being aware of this, it makes sense that we do not need to calculate the indirect illumination for each pixel, but actually calculate at certain points and interpolate in between, therefore reducing computation time. This idea was introduced by Gregory J. Ward back in 1988, talking about the lazy evaluation, or the irradiance caching, as was established as a name for this approach. So, how does it work? We initially generate a sparse set of points within the scene where we calculate irradiance based on pad tracing we talked about. So we don't do it for each pixel. You can notice that the disposition of points is sparser on flat surfaces with less change in lighting and denser near edges where the surface normals are different. And once we have our points set, we can calculate the indirect illumination for all the pixels of our image by shooting a ray through each pixel, hitting a surface, and finding the closest sample points. Based on those and the weighted influence, which we can see here as circles, we can determine the irradiance value. For example, the value B can be done by extrapolating from the current sample E2, value A by interpolating between current samples E1 and E2, and sample C by calculating the new E3 irradiance sample. And while interpolating irradiance from sparse caches greatly improves efficiency, early approaches simply blended based on distance, without considering how lighting actually changes across a surface. This worked well for some cases, but often produced visible artifacts, especially across curved surfaces or geometry with strong light variation, as can be seen here. A better understanding of how light flows across a surface was needed to improve realism without massively increasing the number of cache points. In order to get a better understanding of this, I took this 200 by 200 pixel image of Gregory Ward, which is shown here scaled up, and I wanted to see if I can use the same logic behind Irradiance Caching to color each of these pixels from a scarce sample set. So I generated 1000 samples uniformly throughout the image and sampled the colors from the initial image, storing it for use later. Now, if I took only the nearest sample for each of the pixels I would like to color, which is basically similar to the geometry we would like to shade, I would end up with a pretty splotchy looking image, as can be seen here on the right. Would anything change if we used more nearest samples per pixel? Not really. If we use 2 nearest samples or even 4 nearest samples, the results would become less splotchy but become more blurry as the amount of samples increases. A better understanding of how light flows across a surface was needed to improve realism without massively increasing the number of cache points. So, was this approach doomed from the start? In this current form, definitely yes. Until in 1992, Gregory Ward introduced the concept of gradients into Irradiance Caching. The idea was simple. Instead of storing just the irradiance value at each cache point, gradients record how irradiance changes as you move slightly across the surface or rotate slightly around the normal. This additional information allowed for much better interpolation results because it captured not only how bright a surface was at a given point, but also how that brightness was changing locally. So, how can we understand this? The simplest example would be to take a look at this graph. If we store irradiance values at certain points, the blue polyline would indicate a graph that showcases linear interpolation, so just based on the neighboring samples, like we had previously. But now with the gradients, we can take into account how irradiance changes between samples based on the offsets, which are the local rates of change. This gives us a better prediction of the curve's behavior between points, resulting in the cubic interpolation shown with the red dashed line, and it more closely follows the actual ground truth lighting, the black dotted line, creating a much smoother and more accurate transition, especially in areas with quick lighting changes. But maybe this is too abstract. I know it was for me, so let's go back to our image. We can start by taking our 1000 initial samples, just as we did before. However, we also sample just slightly around each sample, a little to the right and a little upwards, as illustrated here. This gives us a richer local view of how the irradiance or color is changing around each point. Then we calculate the gradients by simply subtracting the irradiance or color value of the offset samples from the main sample in both the x and y directions. And these differences give us a sense of how quickly the value is changing in each direction. So once we have the gradients computed for each sample, we can use them to better approximate the irradiance or color at nearby points we want to shade, like the pixels in our image. And how do we do this? The formula looks like this and presents a simple idea. We use the main sample value and add a small correction based on the distance between the sample and the point we're trying to shade. In other words, if the point is close to the sample, the correction is small. If it's further away, the correction accounts for how the irradiance is changing in space. This way, we reconstruct a much smoother and more natural transition across the surface. So, does that help our initial image? Let's check it out. Even though using gradients greatly improves the result compared to simple interpolation, artifacts are still visible. The image on the right, Irradiance Caching with gradients, looks smoother and more continuous than the pure interpolation on the left, but you can still notice some irregularities and blocky transitions. And this happens because we are still working with a relatively sparse set of samples. So what would happen if we increase the sample count to 2000? As can be seen, higher sample counts tend to remove the artifacts, but there can still be some present. So what if we crank it up to 4000? Gradients can improve how we interpolate between them, but they cannot create detail that was never captured by the samples themselves. So with enough samples, 10% of the total amount of things we would like to shade or color in this case, and we get this result as a comparison. But one thing kept bothering me. They do not use the same amount of samples. The one on the left uses 4000, but the one on the right uses the initial 4000 and then additional 4000 in each of the x and y directions to calculate the gradients. So I wanted to compare the results for the same amount of samples. And this is the result. 12,000 main samples in the image on the left and 4,000 main samples in the image on the right, plus an additional 8,000 samples to calculate the gradients. The question is it worth it? Let's take a closer inspection. While increasing the number of irradiance samples improves the result by brute force, it still leaves the visible splotches and sharp interpolation artifacts, especially across soft gradients and subtle surface changes. On the left, even with 12,000 primary samples, the result looks harsh and somewhat unnatural because linear interpolation cannot smoothly adapt to gradual changes. On the right, even though we used only 4,000 main samples but added Irradiance Gradients, the result looks much more smoother and more natural. The gradients allow the interpolation to follow the natural flow of lighting changes between samples, creating softer skin tones, more believable surface illumination, and better shadowing transitions, which is visible near the nostril, for example. Before I could explain Irradiance caching in a meaningful way, I had to build my own version, visualize the data, and test how it actually works. And that hands-on process, trying things, breaking things, understanding why, was what made it stick. And that brings me to the sponsor of this video, Brilliant. If you didn't know it by now, Brilliant helps you get smarter every day with thousands of interactive lessons in math, science, programming, and data analysis. And it's designed to help you develop real problem-solving skills and not just memorize abstract concepts. And the main reason why is that you're thrown into challenges that force you to think like a programmer, engineer, or scientist. So you don't just learn a concept, you understand how to use it. For me, that's the best part. You learn by doing, by experimenting, and by engaging with ideas visually and intuitively, just like I do when working with lighting systems in real-time graphics. And since the lessons are bite-sized, it fits perfectly into those short bursts of curiosity during the day. So if you're into logic behind algorithms, graphics rendering, or data structures, Brilliant has excellent courses like Thinking in Code, Visual Algebra, and Data Visualization that feel custom-made for this kind of work. So to try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/marquitecta, click the link in the description, or scan the QR code on the screen. And if you sign up, you'll also get 20% off their annual premium subscription. A big thanks to Brilliant for supporting this channel, and now let's dive back into the lesson. Now, since I already made the algorithm for Irradiance caching, I found this beautiful representation in the arcane style, which is, in my opinion, the best looking stylistic representation in animation, and got this result, which was generated using the Irradiance Gradients algorithm we just explored. It colors around 70,000 pixels using only 8,000 samples, with interpolation based on 4 neighboring samples per pixel. Interestingly, the final visual effect, with its soft flowing transitions and patches of color blending into each other, is reminiscent of the techniques seen in Impressionist paintings by artists like Claude Monet. Take for example his San Giorgio Maggiore at Dusk painting. And now, of course, I'm not comparing myself to these masters of painting, but it's fascinating to observe how even a purely technical algorithm can accidentally touch upon the same visual qualities that Impressionists deliberately sought to capture, which is the broken, colorful, and atmospheric look of light dissolving into form. The splotchy aesthetic here isn't just a technical artifact. It carries a certain artistic quality, naturally connecting modern computational methods to classical explorations of color, light, and atmosphere. I even added a Voronoi cell layover to the image to see if it can better depict or create a specific stylistic choice for these types of images. So you can use the word splotchy in the comment below to let me know if you think this has any potential for application with any type of visual content or your images that you would like to try out. But just bear in mind, I made this algorithm with one major flaw, and that is the brute force nature of searching the closest samples for each of the shading points. For example, the 8,000 samples and 70,000 pixels took over 1 minute to compute. So let's go back to our samples and this issue of finding the appropriate samples for each intersection point in our scene, which can become difficult and computationally expensive, since they are located throughout the scene and we have to check all the samples individually. This is similar to the visibility issue when culling triangles, which we mentioned in our lecture about nanite, which you can check out here. So we can implement a similar strategy here. In order to sample these points efficiently, we can organize them in a KD or K-dimensional tree, which is similar to the bounding volume hierarchy, where each point is placed inside a leaf that is always a part of a larger leaf, and so on, reducing the complexity of the search space. Basically, we start with one bounding box and keep dividing it into smaller chunks, thus encompassing all the points in a smaller bounding box until we only have one left. However, if the samples are placed too sparsely or the weight influence is set to be large, splotchy areas may appear, making the end result less desirable for realistic global illumination depiction. So now we had a way to mimic realistic global illumination with Irradiance caching, which is exactly what was used for the movies we mentioned in the intro. But if we're observing Lumen, we have to go away from offline rendering and go to the game engines. So what can we do there? Since the technology and techniques were still far behind for real-time application back in 1990s, the best thing to do was to calculate global illumination beforehand and just bake it into the texture, which is a concept called Lightmaps. And the first game to use it was Quake back in 1996, that originally shipped with pre-rendered light maps that contributed to the overall atmosphere of the game. But light maps had major drawbacks, which is they could hardly be updated dynamically and cannot influence moving objects in the scene. So was there another way to store the lighting information but be able to use it dynamically somehow, which is what we need in our real-time dynamic global illumination? Here we need to talk about the concept of probes and how it all started in trying to answer a simple question. What if we could capture the lighting from a real-world location and use it to light our virtual scenes? This is the exact question Paul Debevec had in 1998 when he developed a method of capturing real-world lighting using high dynamic range photography. So, how does that work? Well, you take a camera and you capture images all around you, 360 degrees, and for every direction you also capture various exposures to get a high dynamic range imagery, or HDRI. Paul Debevec used a different approach. He photographed mirrored spheres or used fisheye lenses. Then you take those images and you stitch them together, projecting the final result into something we call an environment map, which is a full 360-degree representation of light information from all directions, shown here in an equirectangular format. Now, this technique became known as image-based lighting. It allowed artists to reuse captured radiance to light 3D scenes with realistic reflections and shading, long before ray tracing was even practical. Now, capturing and using a single static environment map worked great for indirect lighting and reflections and offline rendering in movies. But imagine that 8K environment map being sampled in real time. It would be just too expensive. So, for real-time engines, we adapted this idea by using environment probes, tools that generate environment maps dynamically inside a scene. An environment probe is a general term for a tool that captures lighting from all directions around the point in space. It gives us a snapshot of the surrounding light in every direction. To store this directional lighting, we use a format called a cube map, which we mentioned in our previous lecture on rasterization-based techniques that you can check out here. As a reminder, imagine standing at a point and photographing the environment in 6 directions, one in each cardinal direction, so front, back, left, right, and up and down. And those images form the 6 sides of a cube, wrapping the scene into a 360-degree texture. Now, each pixel in this cube map stores the light information like color, intensity, which would be irradiance, the total amount of light reaching a certain point. But environment probes also capture the direction from which the light arrives. And this is what we call radiance, directional light energy. So, radiance includes the intensity, color, and direction of light, and is defined per surface area and per solid angle. And this means the light measured depends on how wide the beam is and the angle it hits the surface. As an example, a beam grazing the surface delivers less energy than one hitting it head-on. So, we often use the term environment probes to refer to any probe that captures radiance. But how we use the environment probe defines its type. When it's used for simulating reflections, like on glass, metal, or water, we call it a reflection probe. When it's used for diffuse indirect lighting, it becomes part of a light probe or irradiance probe system. Now, reflection probes simulate specular reflections. They let a shiny surface in our scene reflect its surroundings by sampling the right direction from the reflection probe's cube map. Instead of tracing a real ray, we look up the stored radiance in that direction, giving fast, approximate reflections. But not all surfaces are shiny. Sometimes we just need diffuse lighting, which is light from all directions, basically irradiance, for our surfaces in the scene. So if we sample irradiance from reflection probes, that would be very inefficient because reflection probes store high-frequency radiance, which means all the little changes in the light intensity and direction, which would require many directional samples to compute diffuse lighting, or the irradiance. That's why we can use light probes where irradiance is usually pre-computed or stored separately in a low-frequency format. So how does that work? So let's take a look at our environment map as we turn around in the scene. As we said, it can be difficult to sample from the environment map in real time, so we can generate a couple of probes in our scene, shown here as spheres, and sample our environment map. High frequency for reflection probes and low frequency or blurry for irradiance probes. The question is, how do we get these light probes? Let's take a look at a single light probe, which we will show as a discrete mesh sphere. To simplify, we'll pick one point on the sphere and generate a hemisphere of rays oriented along the point surface normal. We then generate a uniform distribution of sample rays over the hemisphere, where each ray is used to look up light information from the texels on an environment map. So we're not doing ray tracing here, just sampling, which is quick. For each sample, we retrieve the radiance, meaning light intensity and color, from that direction. And to simulate how much that lighting contributes to one surface, we apply a cosine weighted by computing the dot product between the surface normal and the ray direction, which are both unit vectors. Once all the cosine weighted samples are collected, we average the results to get a single irradiance value for that direction. And finally, we repeat this for every sample point on the probe sphere in a process called convolution in order to get a blurry, low-frequency light probe, which is perfect for diffuse lighting in dynamic scenes. So, how does that work? Imagine we have a triangle in the scene rasterized as part of our G buffer in a deferred shading pipeline. From the G buffer, we know the pixel position and surface normal. To compute indirect lighting, we sample the nearest irradiance probe, selecting the value corresponding to the direction closest to our surface normal. And this irradiance value is then scaled by the surface's albedo and divided by pi according to Lambert's law, giving us a fast approximation of diffuse indirect lighting. So no path tracing needed, it's just a smart lookup and a simple lighting equation. To make lighting smoother and more accurate, we don't just use one probe, we interpolate between several. Earlier methods used 4 probes enclosing the surface in a tetrahedron, but today it's more common to use the 8 nearest light probes arranged in a cube around the point, and perform trilinear interpolation to blend their values. And this helps prevent lighting seams and keeps the illumination stable as objects move across probe boundaries. So far, we've seen how we can sample irradiance from an environment map. But what if our lighting isn't image-based at all? What if it comes from point lights, area lights, or other objects in the scene? In that case, we can't rely on an environment map, but we can follow a similar process from before. Use probes and choose sample points, but instead of generating rays for a lookup, we cast rays and do path tracing to compute the lighting, storing the results as irradiance. The result is more accurate but takes longer to calculate than by just doing an environment map lookup. For example, if an environment map lookup takes 0.01 milliseconds for 64 samples and 100 rays per each sample, using path tracing can take up to 0.1 milliseconds on the GPU for just 64 sample rays, so almost 1,000 times slower. And back in 2005, it was even worse. Full radiance sampling could easily take seconds per probe, which made real-time updates completely impractical. So when you want to dynamically change, for example, 1,000 probes in a scene, it can take up around 1 second. So to avoid any delays, you can update the lighting for the probes that are directly around the moving character or geometry and the rest afterwards, working in 32 probes per frame to avoid lagging. So the real-time updates can be doable, but it is not the biggest concern. So what is? Now imagine we tried to store directional irradiance using a cube map, one for each light probe in our scene. How much memory do they really use? Let's break it down. A typical cube map might be 128 by 128 pixels per face, with 6 faces total. That's over 98,000 pixels. Each pixel stores RGB, or 3 floats, which gives us nearly 300,000 floats per probe. With each float having 32 integers, or 4 bytes, that's over 1 megabyte of memory per probe. And if our scene uses 1,000 probes, we need over 1 gigabyte just for diffuse lighting data, just to store blurry, low-frequency lighting. So if you've made it this far, thank you. You are truly devoted to explore this topic to its main essence. And if this video helped explain a piece of Lumen's architecture, consider liking, sharing, or even just leaving a comment like splotchy this. It helps a lot and it lets the algorithm know that real-time GI deserves more spotlight. So is the problem that we're oversampling? Yes, but it's not the biggest issue. The issue is performance. Each lookup involves many texture fetches across multiple faces, which increases memory bandwidth usage and can cause GPU cache misses. Updating these probes dynamically is also costly, requiring high-resolution texture writes. But the irradiance changes slowly. It doesn't need this much data. Like using high-res cube maps for something that's inherently soft and diffuse is a waste of memory and bandwidth. Sure, we can use the lower resolution cube maps, but what we really need is something smarter. A compact representation that's faster to sample, easier to interpolate, and good enough for smooth diffuse lighting. And that's exactly what spherical harmonics are built for. And that's what we'll explore in the next video. So, I thank you for your time and hope to see you in the next video. Bye!